Hello everybody. Recently I was asked whether it's true that every object has the same falling time. So not taking into account the air drag, so let's assume we are in a vacuum and we let an object fall from a certain height h, and what is said that it's really independent of the mass. Both objects, here a leaf and some kilogram heavy object, needs the same time to fall to the ground. So how do we prove this? First we have to do some assumptions. Our first assumption is that the height h is much smaller than the radius of the Earth. And the second approximation is that the mass of the object is the mass of the object which we let fall to the ground. Say we have here the mass m and we let it fall, and it's accelerated by the standard gravity g. So the mass has to be also smaller than the mass of the Earth. In the coordinate system which I plotted here, we have the equation where on the left hand side we have the force acting on the body m, and the force is given by the mass of the object times the second time derivative of the coordinate y. So here, therefore, we have this minus here because it's falling to the ground, and we see immediately that the mass of the object cancels out. So the acceleration is only depending on the standard gravity, and the standard gravity, a reminder, standard gravity g is depending on the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. So in the end, the only mass which appears in this differential equation is the mass of the Earth. And this differential equation can be easily solved by integrating over time. So let's do it quickly. The first integration gives us a constant c0, and another time we integrate and we get c0 times t plus another constant, and this will give us the coordinate of the object depending on the time t. And the two constants, the meaning of the two constants is simple and depends on the conditions, the initial conditions of our problem. So let's assume that the velocity at t equals 0 is 0, and let's remember that the starting height is h, so the other condition is y at t equals 0 is h. We have c1 being nothing else but h, and c0 is the initial velocity, and this is 0. So we end up with the function which is this one, and this allows us now to find easily the falling time, which is, let's write it down again, which is given by the equation where the coordinate reaches y equals 0, and yeah, this gives us now the falling time t0, which is twice the height divided by g. And let's take the positive square root because the time is positive. So our conclusion is that the falling time is proportional to 1 over square root of the mass of the Earth alone. Thus it's independent of the mass of the object, which was m. So what is the mistake or the assumption we made here? The assumption is that we assumed the system to be an inertial system, but to be precise, it's a two-body problem. So we have here the mass of the Earth and the mass of our object with the mass m. And what happens now if the assumption that the Earth mass is much larger than m is not fulfilled? So let's do the precise calculation, and let's put our coordinate system in this way. Here let's take an x-coordinate, and the center of the Earth, let's assume it to be a sphere, is at the position x1, and the mass m has the position x2, with the center of the coordinate being here. Let's assume here x2 being larger than x1, and define the distance between both to be x2 minus x1. Each object, so the Earth and the mass m, exerts a force on the other one, which is F equal to gravitational constant times the mass of the Earth times the mass of the object, small m, divided by the distance between both objects, which is here r squared. Both masses exert the same force concerning the modulus of the force, but the force is, of course, acting in a different direction. That means, let's look at the acceleration of the Earth. So this is given by the mass of the Earth times the second time derivative of the coordinate x1. And this is pointing into the positive direction according to how I set the coordinate system here. And this is ng times me times the mass divided by r squared. For the object with mass m, we have a negative acceleration, so it's pointing in the minus x direction, and here it's the coordinate x2 and has the same modulus of the force. And the first thing we can simplify now is cancel out the coding masses and add both equations. So I add this equation to this one, and we end up with G, and now we have here the sum of both masses divided by r squared, which is on the left hand side nothing else but minus the second time derivative of distance between these two objects, so this here. And finally we arrived at the differential equation, which we can use now to precisely calculate how mass m is falling towards mass me, or vice versa. So the next step is to solve this differential equation. But before we solve this differential equation, let's first compare it to our first result, which was minus g equal to the second time derivative of y, which is g times the mass of the Earth divided by the radius of the Earth squared minus y dot dot. So we see that there are two assumptions made. First, the force is not depending on the height, so it's simply because the height which we assumed at the very beginning, from the height from which the object is falling, is much smaller than the radius of the Earth. This was the first assumption, and here you see the second assumption. Here we have only the mass of the Earth because assumed this condition to hold. And from the form of the differential equation, this one, we can immediately say that the falling time, we called it t0, will be a function which is proportional to 1 over square root of g times the sum of Earth of mass and the object with the mass m, times a function which depends on the initial distance between both objects and the final distance, so the distance where both collide. To see the mistake we did it in our very first approach, we can Taylor expand t0, and the Taylor expansion is respective the ratio between m and me, which is assumed to be much smaller than 1. So this allows us to write down the expansion up to first order in this small quantity, and since the function f is simply a prefactor, we can put it in front. And here comes the theta expansion of 1 over square root, which is 1 over square root of g times the mass of the Earth times 1. So this is the zeroth order, plus the first correction, which comes with a minus 1/2 multiplied by the ratio between the small mass and the large mass times 1 over square root of GME plus higher order of terms which have the ratio between the small mass and the large mass. And as a conclusion, we can see that the first term is completely independent of the small mass m, and we get the first correction which is proportional to the ratio between the small mass and the large mass. That comes with a minus. That means that the falling time is smaller when we do the exact calculation. And in the next video I'm going to solve this differential equation exactly. So far so good. Thanks for watching this video and see you next time.